Hi, it's Paul Anderson, and this is Chemistry Essentials video 007. And it's on the quantum mechanical model. In other words, it's going to be our current model of what an atom looks like. Before we had this quantum mechanical model, we had what was called a shell diagram. And so when you look at neon had 2 electrons in the first shell, and then it would have 8 electrons in the next shell. And we figured that out by looking at spectral data. And so what we've discovered since then is uncertainty in those electrons and a little bit more of the characteristics of electrons. And so this has kind of been replaced with a quantum mechanical model. Now the shell model works great at making predictions, and so does the quantum mechanical model. They're just different theoretical concepts of what an atom looks like. And so our shell model really is based on Coulomb's law, which talks about the interactions between protons and electrons. But there's a couple of things about electrons that we discovered. One was the uncertainty principle. In other words, when you're looking at an electron, the act of light bouncing off of that and coming back to you changes the momentum of the electron. So you can never know both the location and the momentum of an electron. There's uncertainty there, and so they live in these clouds of probability. And so since they don't follow specific orbits, we came up with this new term, which is an orbital, which is where they're going to spend their time. Another important thing about electrons is that they have spin. So they're going to either have a clockwise magnetic spin or a counterclockwise magnetic spin. And as a result of that, you can only have 2 in every orbital. And so we really had to throw out this idea of the shell, or at least modify it so it fit with the data. And so now we have this quantum mechanical model, and we can use complex equations and computers to develop software that predicts how atoms are really going to interact. So Coulomb's law, remember, predicted where electrons are going to be. You have these positive charges on the inside, and you have these negative charges of the electrons. And so the larger these charges get, the larger the force holding them together is going to be. But as they move away, as the radius increases, we're going to decrease that force. But there's 2 problems with that general shell model. Number one, they don't flow in these specific orbits, and that's because of Heisenberg's uncertainty principle. And then the other one is that spin means we can only have 2 electrons in every orbital. And so this idea of 8 in one shell is just not going to work. And so there are these orbitals. And if we start on the inside, the first one's going to be called the s orbital. And then we move to these things, which are polar. And so we call those the p orbitals. They don't come from polar, but that's how I remember it. Then we move into the d orbitals, and then we move into the f orbitals. I don't know if I have those, but essentially they're all of these clouds of probability where electrons sit. And so we have what are called quantum numbers, and the first 3 are going to determine what that orbital looks like. So the first one is going to be n, and that's going to be the size of the orbital. As n gets larger, then that area of which those electrons are going to be is going to get larger. We next have L, which is going to be the shape of that orbital. It could be an s, a p, a d, or an f. Then we move into the orientation, which is going to be m sub L. And so S can only have 1 orientation. P can have 3 orientations. And so it just goes 1, 3, 5, 7. And so when we're adding in the orbital diagram, as we're adding electrons to it, we're going to put a lot more electrons in the orbitals of the F subgroup than we are of, for example, the P. And then there's going to be the spin. And since those electrons have spin, it's counterclockwise or clockwise, we can only put 2 in every orbital. And so what we can do is we can develop Schrödinger's equation is an example of that, that's going to predict where these electrons are found. And by doing that, we can predict not only what an atom looks like, but how atoms are going to interact. And it's so complex that lots of times we need computers to do the math. And so did you learn how the quantum mechanical model can refine the classical shell model? Well, I would point you to these 2 things, uncertainty of the electrons and the spin. And it's not like we throw out the shell model, it's just that we're getting better and better models of what an atom looks like based on the data that we're getting. We'll talk about that in the next video, but I hope that was helpful.